Welcome to the exciting adventures of aromatic chemistry. So what we've got to do over the next kind of 10 hours worth of lectures, we're going to cover some aromatic chemistry and some carbonyl chemistry. And these are two key functional groups that you will see appear in lots of different drug molecules. So we're going to start with the aromatic chemistry, and then we're going to move on to the carbonyl chemistry. So we've got today and tomorrow, I think Thursday afternoon, of aromatic chemistry, and then Friday we'll start on the carbonyl chemistry. Now, the carbonyl chemistry slides aren't up yet, and that's because I'm trying something different in this lecture, in which I'm going to see whether I can draw the mechanistic work on my tablet and show it on the screen. So before I release the carbonyl chemistry, because depending on whether this works or not will depend on which version I release to you. So we're going to have a go, and then by the end of today, all of those lecture slides will be there. So the reading list, I mean, we've mainly taken all of this work from one book, which is a very useful one, and it's the Essentials of Organic Chemistry for Students of Pharmacy, Medicinal Chemistry and Biological Chemistry, and it's by Dewick. Now, we have lots of copies of that in the library, and we also have it as an ebook, so you should be able to access that. So anything I'm saying to you, if you think, I have no idea what Dr. Race is talking about, take the lecture notes, go and have a look in the recommended textbook, and see if that can help you to understand it. So what are the aims of what we're going to do for the next hour or couple of hours? Well, first of all, we're just going to kind of introduce the concept of aromaticity. Again, for most of you, hopefully this will be a recap. Okay, we're going to recap the structure of benzene and aromatic rings, and just very quickly think about how does it compare to the alkenes that you did with Dr. Page's last week. We're then going to look at a specific type of chemical reaction that aromatic rings undergo, so that's electrophilic aromatic substitution, and hopefully understand the mechanism of that. Based on that mechanism, we're going to look at three kind of fairly simple, fairly useful modifications that we can make. So we're going to look at how to introduce halogens, how to introduce a nitro group and a sulfonyl group. Again, these are key groups that you see appearing in lots of pharmaceutical products. We're then going to look at how to do something a little bit more complicated, and that's to following a very similar reaction mechanism, but we're going to try and introduce alkyl groups or acyl groups. So we're going to start doing carbon-carbon bond formation. And then finally, we're going to think about, with aromatic rings, what we're going to look at to start with is a simple one, when it's just a benzene and we're adding something to it. What happens if it's more complicated? What happens if you've already got some substituent, some other group on your aromatic ring already? And what we'll see is it changes the reactivity, and it changes the final product that you might get. So just to kind of reiterate this, you know, the question I always like to ask is, what do the following drugs have in common? And there's a whole load of drugs there. Some of those you will know, some of them you may not. Many of them you should hopefully know by the end of your course. But the key thing about them all is that they have aromatic rings as part of their core structure. So ibuprofen, aspirin, paracetamol, those simple painkillers that people use every day, predominantly are based around an aromatic ring with different substituents coming off of it. So you might ask yourself the question, why are we learning about aromatic chemistry? Well, the answer is some of the most widely used drugs contain aromatic rings, and we need to make sure we understand how they change the important parts of their structure, their reactivity, and equally understanding how simple or not simple it is to make them. Because that, again, kind of helps us to understand why these very, very simple drugs, well-used drugs, don't cost a huge amount. Because the chemistry we really understand, and we can make these things very simply in big quantities. So before we look at aromaticity, I just want to take you back to hopefully something which you've all done before, whether that's A-level, whether that's BTEC, whether that's Access Foundation, but the idea of just going back and looking at delocalization, because delocalization of electrons is absolutely key to understanding what happens in aromatic systems. So here I've given you a couple of examples of various pi-containing molecules. So we've got various combinations of pi electrons, double bonds within this molecule. And I just want you to kind of remind yourself, what does delocalization mean? Okay, so delocalization is where we can take those pi electrons and we can spread them across more than just one double bond. So if we take the first example up here, okay, if we think about what makes a pi bond, and if you go back to Dr. Ullman, she taught you about sigma bonds and pi bonds, and she would have explained to you that pi bonds are formed by those p orbitals, the unpaired electrons in p orbitals, which can then overlap. So if we draw in our dumbbell p orbitals, okay, what we are saying is you have a double bond across here, and you have a double bond across here. Now, of course, hopefully you're looking at that saying, well, why does it have to be across here and across here? Why can't we form a double bond between these two p orbitals? And that's the right thing to ask, because the answer is, well, we can. So just because we've drawn it with these fixed double bonds, what we have to start to appreciate is that maybe isn't the true story. There is the ability to move those electrons around. And so what we can actually say is that these are a series of interconnected p orbitals, and that can allow the electrons to delocalize, to be shared across all four atoms. So we've got partial double bond character between all of these three bonds. So they've all got a clear, straightforward sigma bond, but then all three of them have this pi bond character. It's a delocalized system. And what it does is it provides added stability. If you think about it, the electrons being concentrated in one area, we know, because we've looked at some reactivity already, if you have electrons based in one area, that makes them potentially neutrophilic. It makes them more reactive because all those electrons are bunched together. To spread them out helps to stabilize, helps the charge, the repulsion of the electrons to be further away. So it's a good thing to be able to delocalize. And if we look at some of these other ones, can we do that? Well, here we have a double bond, and here we have a double bond. Now, this is where I'm going to try drawing and see whether it works. So, if we think about drawing the p orbitals in on this one, let's see, are we going to get it to work? No, that's not what I want. No, not going well. There we go, right, we want to draw. Okay. Pen. Right. So if we draw our p orbitals, okay, we can see that we can have those two, but we don't have a p orbital on this central carbon. So there is no way we can form this kind of delocalized system here, because there is no p orbital on that there. We can do the same thing here. Look, we've got our p orbitals here, p orbitals here. We've got our double bonds kind of across here, but we now have, there's no carbon in between these, so again, we can form that delocalized system. Okay? So we can see a little bit about how that works. Now, because I've talked to you for, what, 5 minutes now, 10 minutes, I can see a few of you are starting to glaze over. It's 9 o'clock in the morning. So I'd like to give you a little break, but I like to make you think while we're doing it. So what I need you guys to do is what I call a 2-minute test. This is just your chance to stop listening to me and have a go. Make sure that you understand what I've just told you. So what I want you to do is look at these two examples and work out, are these delocalized or not? Okay? So have a go at that.